Hello everybody. So in this video we're going to start one new chapter in the textbook, which is about the momentum analysis of fluid or flow systems. This is going to be a different topic from what we were discussing last time or last chapter, and it's going to cover one new aspect of the fluid dynamics, which is an interesting thing to know. So, in chapter 5, we were interested in discussing or studying the fluid flow, and to analyze how the fluids flow. And to do this, we use two types of equations: the conservation of mass and conservation of of energy. And we were able to use these two equations together to understand how the fluid is flowing and to predict how the pressure will change or how the velocity will change from a point to another. However, in this chapter, we are more interested in how this fluid flow is going to affect the surroundings to this fluid. By this surroundings, we mean the pipe walls, any surface, any thing that is exposed to the fluid while it's flowing. And this is important as we need to design systems that are suitable for this fluid, and they can accommodate or can withstand the forces that are generated due to the flow of this fluid. Okay, so this is a very important point. And what we're going, by the way, what we're going to do in this chapter, as I do all the time, I will start with an introduction to the topic, and then the governing equations, and then the applications of these equations. So I'm making this video just to concentrate or focus on why we are studying this topic of the linear momentum equation, or the momentum analysis of flow systems. And the reason I will focus here on this point is that the goal of this chapter is not, for me, at least for me, is not well discussed in the textbook. It took me some time to understand why we are doing this, and what is the motive of this study. So I wanted to make it easy for you when you go through this chapter to understand why we are studying this and what is the final goal that we want to achieve by going through this. So we already have discussed before the forces that arise due to the static fluids, and we said if we have, let's say, a tank that is filled with a liquid, then there are forces that will be generated due to the pressure of the fluid or this liquid due to the fluid head. And we said that the force is equal to pressure times area, and the pressure is the external pressure plus rho gh. So as we go down, the pressure will increase, and this is something that we discussed before. And we said that this is important because we need to design, whether we're designing a submarine or a dam or storage tank or whatever system that will be dealing with static fluids. Now, when we go through the other case where we have a flowing fluid, so the forces that will be acting on the walls of the pipe or whatever the channel that this fluid is flowing in is not only the pressure. There is one more force or type of force that will be generated, which is due to the momentum of the flowing fluid. The momentum of the fluid is or generates a lot of forces, and the knowledge of these forces is very important, or being able to calculate these forces is very important, because we need to design the system accordingly. So this is something that we can see. For instance, here in this video we have firemen that are getting trained on using the fire hoses to extinguish fires. And you see here they are holding these are the hoses. They're long hoses, of course, and each one of them is holding a hose, and they're going to get trained on holding the hose and pointed towards the fire. So you see here this fireman here, once the water, you can see the water flowing in the hose, and once the water reaches the hose outlet, he's like flying away with the hose. And this motion that is generated, or that you see here, is due to the momentum of the fluid. So of the water. So the water is flowing with very, very high velocity, and this high velocity generates a lot of momentum, which results in a lot of forces that can push him backward, or can break things, or do damage to things. So it's very important to know how much forces this, so you can plan accordingly. You can, whether you are going to hold it in place, you need to know how strong you need to hold it with, or how much forces you need to hold it with, or whatever. If you want to have a similar, maybe a sprinkler or something that is fitted to a wall, how many bolts you're going to use, and how thick, or what's the diameter of these bolts. This all depends on how much forces are generated due to the momentum of the fluid. One other thing is that we can make use of this huge force of the momentum, due to the momentum. And one application is the water jet cutting machine. It's a cutting machine like any other cutting machine, but it uses water. A water jet that is very thin jet, so it generates very high pressure at the point that is affecting it, and it's at very high velocity. So this high velocity generates the a lot of forces, and you can see it's breaking it's cutting through that base, and it's now cutting through the metal lock, and you know how strong these metal locks are. So it requires a lot of forces. This is not laser. This is not like a cutting machine that is using metal cutters. It's just water. So this is the forces that are generated because of the velocity of the water are huge, and they can be very, very strong, that they can do a lot of damages. So this is something that we can express using the laws of physics that we know. So this is or this can be explained using the second law, the Newton's second law, which says that the acceleration of a body is proportional to the net forces acting on it, and is inversely proportional to the mass, which we can express using this equation. It's F equals ma, and it's a very, very well known equation. It's expressed here in another way. The text here states that the acceleration is directly proportional to the force and inversely proportional to the mass, which is F equals ma. It's the same thing. We can rewrite this equation. Of course, this is a vector equation. We have here force is a vector and acceleration is a vector. So it has three components in the three dimensions, whether it's x, y, and z, or r, theta, and phi, or r, z, and theta, according to the coordinate system that we are using. But this is a three-dimensional equation. And we can write the acceleration as the time rate of change of the velocity. And we can combine this with the mass, so it's going to be the mu by dt. Mu is the acceleration, the momentum. Okay, so this is the momentum of the body. So we can write the same equation as the force is the rate of change of momentum of the body. So we can say that the rate of change of momentum of the body is equal to the net forces acting on the body, and this is called the linear momentum equation. So this is what we call the linear momentum equation. And if the summation of forces is zero, then the derivative is zero, and this means that the momentum is constant. And this is referred to as the conservation of momentum equation. And this is something that we can see with a very, very famous setup, which is called the Newton's cradle. I think it's a very well-known setup, but it's a set of metal spheres or metal balls that are hanged from the top, so they can freely go in the horizontal direction. Okay, and as you see, you can move one of the balls. You can pull it, and once it's left, one ball is hitting here, and the momentum is transferred to the left side until the one ball moves from the other side. If it's multiplied to be two balls from the right that are left, then two balls from the other side, the momentum, which is momentum of two balls here, is transferred to the same amount on the other side. If it's three balls, then it's going to be three balls also going to the right and to the left. So this is it shows the conservation of momentum in a very clear way. Okay, so the equation that we just saw, which is the conservation of, I mean, the linear momentum equation, is, as we said, is a vector equation. So it can be either written in the way we have here, which is F vector equals d by dt of mu vector, or it can be written as three separate equations. Each one of the equations is in a specific direction. So we can have forces in x direction equals the rate of a change of momentum in x direction. For y direction, the forces is the rate of momentum or rate of change of momentum in y direction, and the same for z. And this is what we're going to be applying, inshallah, in the equations that we will solve in the end, or after we go through the derivation of the equation. So this is all what I want to say here in this video. I hope the motive of this chapter is clear now. And inshallah, starting next video, we are going to start with the governing equations and write a more detailed or reach a more detailed form of the linear momentum equation. So I'll see you then, inshallah. Goodbye.